Welcome to the debate. Our focus today is on some really comprehensive new neuroscience research studies that have looked at the failure of damaged axonal isolation, or demyelination, from four distinct and interlocking dimensions: structural, temporal, molecular, and computational.
And that multidimensional view is so critical because it really moves us past this simplistic idea of just a signal slowing down. It forces us to ask a much harder question. Among all these different ways a neuron can fail, which one is the fundamental breakdown? Where does the whole system truly collapse?
Exactly. So the central question we're facing is this: is the primary impairment a functional one? The loss of the temporal precision you need for coding and for network synchronization, or is it something more physically absolute? I'm going to argue that the essential failure really is in that breakdown of timekeeping.
And I'll be arguing that the functional breakdown is just a symptom, a consequence. The core issue is the non-negotiable structural and mathematical limits that get placed on signal propagation. I mean, if the physical capacity of the axon collapses, then the primary problem has to be the structural and computational entropy of the wire itself.
Okay, that's a crucial way to frame the mechanism, but I think it misses the primary consequence that actually defines the pathology. When we look at, say, the high-stakes layer 5 corticothalamic projections, the L5 to POM pathway, this is what coordinates long-range activity. And the key functional problem with damaged isolation is the failure of precise timing. It's undeniable. The evidence from the Jamamin and Coley group leaves, well, very little room for ambiguity. Demyelination dramatically increases not just the spike delay, but crucially, the jitter, the variance in when a spike arrives. We're talking about conduction velocity plummeting from a healthy 1.1 meters per second all the way down to a sluggish 0.35. That creates a significant 4 to 5 millisecond delay, and that is more than enough to destroy the precise ordering of events. The receiving thalamus just can't read the input anymore.
I respect the temporal argument, I really do, but it defines the problem by its function, not its physics. The timing issues you're citing are the observable symptoms of a much deeper physical and mathematical breakdown. You can't prioritize the timing of a signal that the wire itself can't reliably carry in the first place.
Okay, but
Just think about the computational evidence. Myelin loss acts as a definitive low-pass filter. This isn't just an observation. It's a mathematical truth. Our models prove that high-frequency bursts, the rapid trains of activity over 100 hertz that these L5 neurons use to communicate, they physically cannot pass through a demyelinated axon. It's an information ceiling. If the most important information is filtered out, whether the rest of it arrives 4 or 5 milliseconds late it's a secondary detail.
I fully agree that the computational models reveal a fundamental physics problem, but we have to ask, what is the ultimate operational failure? The entire system is built for high-fidelity temporal coincidence detection. The functional impairment we see isn't just conduction block, it's massive jitter and increased variance in the spikes that do manage to get through. And that variance is what truly scrambles the code.
Professor Coley described this perfectly. He called it the loss of the first black stripe of a neural burst. If you think of the neural message like a barcode, the scanner, in this case, the thalamus, it needs absolute precision. That huge delay and variance means the input becomes unrecognizable. So we are measuring a coding failure, not just a transmission failure.
But the coding failure is a downstream consequence of structural chaos. The physical breakdown is just relentless. To try and maintain excitability with all that lost insulation, the system attempts damage control, and it fails miserably. We see really compelling evidence of this structural and molecular chaos and how the axon physically restructures itself.
Right.
Specifically, the axon initial segment, the AIS, the neuron's decision center, it physically moves. It relocates about 2 micrometers closer to the soma. This is the neuron literally moving its own goalposts out of desperation. And what's more, the molecular organization just dissolves. Ion channels like Na1.6 and KV7.3, which are supposed to be in these tight clusters at the nodes of Ranvier, they just detach and spread out. You're left with a physically and molecularly disorganized, leaky pipe. That is a structural failure that causes the temporal problems you're measuring.
I see the structural argument. The hardware is clearly degrading. But let's go back to the primacy of information integrity. You're focused on the maximum capacity, the loss of that 100 Hz burst. But I'm focused on the minimum required reliability of the signals that do get through.
Okay.
The low-pass filtering might prevent the highest frequency bursts, sure. But the critical functional degradation is the timing instability of the individual spikes. The empirically measured delay and jitter that we see in the in vivo experiments, that's the honest scale of biology measuring the damage. This temporal entropy, this loss of control, it means the system literally cannot synchronize its inputs. Coincidence detection is the fundamental language here, and demyelination makes it impossible to speak it.
The destabilization, that physical restructuring we see, that AIS retreat of 2 micrometers, is an irreversible structural change. The AIS doesn't move for convenience. It moves because the electrical properties of the exposed axon have become so chaotic that the neuron has to physically relocate its firing site just to initiate a spike at all. That physical retreat and the dissolution of the ion channels, that's the cause. The timing loss is the symptom.
And yet, we can measure the functional consequence of that delay. That 4 to 5 millisecond delay is the functional reality. It forces the receiving brain region, the POM, to dramatically widen its temporal integration window. Just think about what that means. It blurs the very perception of now. The network's ability to coordinate anything is undermined because the input timing has too much variance. This functional blurring translates directly into cognitive failure.
And this brings us right to the computational framework. You're relying on the empirical measure, but to understand the absolute limits, we have to rely on advanced models. The sources themselves highlight that the simpler Hodgkin-Huxley cable theory, it fails for thin geometries. It has a limit. To really capture the complexity of ion movement through a damaged membrane, we need electrodiffusive modeling, specifically the Poisson-Nurse-Planck model, the PNP model. It's like a digital twin of the neuron, and it confirms the physical constraints. The low-pass filter effect is mathematically unavoidable. The structural limits define the operational ceiling.
Okay, while the PNP model gives us resolution where the classic cable theory struggles, it is still a model. It's built on complex assumptions. The empirical timing data that measured 4 to 5 millisecond delay and the increased variance recorded in vivo, that is the ultimate test. It's the real-world measurement. We know this temporal blurring happens, whatever mathematical framework you use to simulate it. The computation confirms the mechanism, yes, but the primary functional loss is the destruction of the temporal code.
But we can't ignore the molecular dimension, which points to a level of structural failure that is, well, existential for the axon. It goes far beyond timing errors. Damaged isolation exposes the axon to external chemical noise. The work by Hamada and Kabele showed that losing myelin leads to ectopic action potentials, spontaneous, uncommanded spikes generated by the exposed axon just reacting to potassium in its environment. So myelin wasn't just for speed, it was protecting the wire from noise. When that integrity is gone, the signal initiation itself becomes chaotic. The neuron starts telling lies. And on top of that, we now know that sodium channels are actually permeable to calcium. In a healthy system, that's managed. But in a hyperexcitable, demyelinated system, Hahnemeyer et al. Show that this can lead to toxic calcium accumulation inside the axon. This is not a timing error. This is an existential molecular threat to the axon survival, period.
That is a compelling point about molecular integrity, and I agree. Calcium accumulation and ectopic spikes are profound architectural failures. However, the purpose of the system is functional communication, which it achieves through synchronization. Ectopic spikes just add more noise to an already scrambled temporal code. If the fundamental language of the brain is the temporal ordering of events, then the molecular chaos, it's just another form of input corruption. The fire that burns the network's ability to coordinate remains the loss of temporal fidelity. The axon is generating lies, sure, but it's generating them into a system that has already lost its ability to reliably read the truth.
And I maintain that the molecular chaos and the physical retreat corrupt the very source of the signal. If the axon is generating spontaneous signals, the functional integrity of that neuron is broken by structural and molecular entropy. Timing loss is just one of many consequences of this deeper collapse in the structural foundation. The chaotic state of the demyelinated axon makes reliable propagation computationally impossible, structurally chaotic, and chemically toxic.
In the end, the comprehensive evidence confirms that without that protective layer of myelin, the system loses the essential ingredient for high-fidelity information transfer, the precision of time. The measurable jitter and delay destroy the network's ability to engage in coincidence detection, leading to a state where the temporal code becomes functionally unrecognizable, and that manifests as profound network dysfunction.
And while the measurable outcome is compromised timing, the structural and computational views demonstrate that the axon enters a state of entropy, where signal integrity collapses first, the physical retreat of the AIS, the dissolution of molecular organization, and the mathematical proof that high-frequency signals cannot even propagate define the foundational failure, the chaotic physical state where the signal fails before it even has a chance to be timed at all.
We have explored the multidimensional evidence, structural, temporal, molecular, and computational, of demyelination failure, demonstrating that, well, this level of complexity often requires multiple perspectives to fully appreciate the profound consequences of lost insulation on neural function.